Hey, Mr. Noldy coming back at you. Have a calculus problem to show you today. Specifically, it's an optimization problem. So it is going to require taking derivatives. Kind of a simple problem. It has, it's contrived, it works out very nicely. But if you can learn how to work these, then everything else will kind of come into place in the future. So here's the problem, getting it out of our calculus book here. So it says, it's a minimum length problem. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 245,000 square meters in order to provide enough grass to feed the herd. No fencing is needed along the river. What dimensions will require the least amount of fencing? All right, so I get to draw a little bit here. Got the book on my keyboard. All right, so we have a river, so I'll use blue to, this is like a river, okay? Because water's blue. So here's our river, and we're gonna build a rectangular pasture. So it's gonna look something like this, right? Something like this. So, and it doesn't need any fencing along the river. So I have to pick a few variables here. The only thing I know for sure is that the area has to be 245,000 square meters. So let me come up with some variables here. Let's call this one, I'll call it X, I guess, because it's going in the X direction. And we'll call the sides Y. So this is an example where we need to have two equations, a primary and a secondary. So the primary equation, that's the one that we're going to take the derivative of. The secondary helps us to somehow replace these variables because we're only working in one variable here. So my primary equation, if I wanted to minimize the fencing, so that means I want to minimize this green perimeter here. So that's going to give me, let's see, the perimeter. I'm going to write it inside the pasture here. So the perimeter is going to be 2y plus x, because there's two y's here, and there's one x here. So that is the equation that we're going to use to minimize this. So I don't like looking through my fence, so I'm going to erase it a little bit here, if that's okay, just to move it up a little bit, so I don't feel like I'm staring through the bottom of the fence. All right, that's more gooder. All right, so this was our x. So the perimeter equals, I guess I'll start with x. I wrote it the other way before, but it doesn't really matter. So this is known as the primary equation. We're trying to minimize what's going on with the perimeter. So notice we have an x and we have a y, so we can't really do that. So we have to default to a secondary equation, and that is this area. So the area is going to be, well, it's got to be 245,000. So x times y equals 245,000. So this is the secondary equation. And the secondary, forgot a zero. The secondary equation, we solve for y in terms of x or x in terms of y. Okay, 2 times 245 I know is 490. So I'm going to solve this for y in terms of x. So that would be 245,000 divided by x, or x to the negative 1 if we prefer. So over here, we're going to substitute 245,000 divided by x in place of y. So let's continue with that. So x plus 2, well, what is 2 times 245? I might as well go straight to that. I think that's 490,000. Check me on your calculator if you don't mind. And I'm going to move the x upstairs to make it easier to take the derivative. So we want to minimize. So anytime you read a word problem that's about minimization or maximization, you're looking to take a derivative. So the first derivative of this would be, let's see, the derivative of x is 1. Negative 1 times 490,000 is negative 490,000. And then this would leave us with x to the negative 2 up here. So to find the relative max or mins, we set this equal to 0 and then solve it. So if I set this equal to 0, 1 is going to be equal to 490,000 x to the negative 2. So to solve this, I'm probably going to want an x to the positive 2. So can I go ahead and put x to the positive 2 downstairs here? Is that okay? We're allowed to do that, right? So it's a proportion, so just cross multiply to solve it. So that leaves us with x squared equals 490,000, and which I saw was a perfect square when I started to set this up. So once you do these a lot, you're going to start to see patterns. So when I take the square root of both sides, square root of 49 is 7. There's 4 zeros, so it's going to have 2 zeros. So we suspect that 700 is the minimum. We can verify that by taking the second derivative. So let me go over here and do a second derivative for p. Is that going to fit on the screen? The second derivative of p. So the derivative of 1 right here, that's going to go to 0. Take negative 2 times negative 490,000. That is going to give us what? 900, positive 980,000. Got enough zeros? Yep. And that's going to bring it down to x to the negative 3. So what you want to do to determine whether this value is a minimum or a maximum is substitute it into the second derivative to see if it's positive or negative. So that would give me 980,000. I'm going to make this x cubed in the denominator, so that would be 700 cubed. And at this point, I don't even have to figure this out because I know it's going to be positive. So this is greater than 0. So, oops, that's not a good greater than sign. So whenever the second derivative is positive, that's going to indicate that it is concave up, remember? And if it's concave up, then it's got a relative minimum. So I know this is indeed a minimum. So my 700 kind of checks there. So now I got to go back over here to the secondary equation. And the secondary equation, y equals 245,000 divided by 700. So let's go in and figure that out. 245,000 divided by 700. And let's see, when I do that, I get what? 350. So we're looking at this distance being 700 feet and this distance being 350 feet. No, and this distance is 350 feet. So the final question was, what's the minimum amount of fencing the farmer has to buy? So we have 350 plus 700 plus 350. So that's 700 and 700. That gives us 1,400. So he's going to have to buy minimally. Let me put that in a different color so it stands out a little bit better. It's going to be 1,400. So minimum fencing, hopefully we can all read that, is 1,400 feet of fencing. So, or meters, whatever the, yeah, I guess it was in meters. So meters. A little bit sloppy there, apologize for that. So again, to recap here, we make a picture of what it is we know, and then we always have a primary equation. Sometimes there's not a secondary equation, but when I get a primary equation, I see I have two variables because I'm not doing two variable calculus right here. I have to go to a secondary equation. I solved this for y, got the y in terms of x up here. This is when I was checking. Up here, 245,000 divided by x, substituted it in for y over here. When I multiply by 2, that's where the 490,000 came from. X to the negative 1 to make it easier to differentiate. Derivative of x is 1. Negative 1 times 490,000 is negative 490,000, and then we decrease the exponent by 1. Then I set it equal to 0, solve for x, I get 700. Technically, I would get plus or minus 700, but I can't have negative 700 feet or meters of fencing here, right? So 700, and just to be safe, we took a second derivative to see if we had an actual minimum, and we did, because the second derivative at 700 turned out to be positive, so that indicates that part of the curve would be concave up, so it's a minimum, so that checks. Then we go back to the secondary equation, substitute 700 in place of the x, and we get 350. So 350, 700, 350, all added up to 1400. So there is a quick and dirty look at an optimization problem. So they can get a lot more tricky than this, and let me know in the comments down below if you'd like to see one that's even more tricky. But I just wanted to show something basic tonight just to give you the overall picture of what's going on. So hopefully you got some value out of this. If you did, go ahead, like and share. Share it with some of your classmates. And in the future, make sure that you are always doing your assignments, okay? Practice is the only way to get good at math. So we have to practice, practice, practice. So until the next time, Mr. Noldy here, signing out.